Keep low! Incoming!
The wind hit at 160 miles per hour. Metal tents flew through the air like paper. Wooden barracks exploded into splinters. Men screamed as roofs tore away above their heads, exposing them to rain that felt like bullets against skin. This was Espiritu Santo, October 1942. A typhoon nobody saw coming had just turned an entire American military base into a graveyard. Sergeant Mike Crawford grabbed onto a support beam as the storm ripped his shelter apart. Around him, soldiers scrambled for cover that didn't exist anymore. Equipment worth millions gone in seconds. Medical supplies, ammunition, food rations, all swallowed by wind and water. But the real problem wasn't the supplies. It was the men. 12 soldiers died that night, crushed by collapsing structures, drowned in flash floods, struck by debris moving faster than cars on a highway. By morning, the base looked like a war zone, except the enemy wasn't Japan. It was nature. Commander William Hayes stood in the wreckage at dawn, water dripping from his helmet. Around him, what used to be housing for 3,000 troops now looked like a junkyard, twisted metal everywhere. Shredded canvas flapping in the wind. Men digging through rubble, searching for survivors. Hayes had a bigger problem than rebuilding one base. The U.S. military had just committed to island hopping across the Pacific, thousands of miles of hostile territory where typhoons hit regularly. They needed shelter for over 100,000 troops. Shelter that could survive 150 mph winds. Tropical heat that cooked men alive. Torrential rain. And oh yeah, Japanese bombs. Every existing design had just failed catastrophically. Standard military tents, shredded in minutes. Wooden barracks, kindling. Metal Quonset-style shelters they'd been testing, half of them buckled under pressure. The other half turned into ovens during the day, baking soldiers at temperatures over 120 degrees. Men couldn't fight if they were dead from heat stroke, or crushed by their own shelters, or exposed to enemy fire because their cover blew away. Hayes sent an urgent message to command. Current housing solutions inadequate, requesting immediate engineering response. Casualty rates from environmental factors approaching combat losses. Translation: the Pacific weather was killing as many men as the enemy. Back in Washington, military brass received dozens of similar reports from across the theater. Guadalcanal, New Guinea, the Solomon Islands. Everywhere the story was the same, troops dying because nobody had figured out how to build shelter that could handle what the Pacific threw at it. This wasn't just about comfort. This was about survival. A soldier named Private Tommy Chen wrote home 3 days after the Espiritu Santo typhoon. "Mom, I survived the storm, but Jackson didn't. A support beam crushed him while he slept. They're telling us new shelters are coming, but I don't know. How do you build something that can take this kind of beating?" His mother never received that letter. Chen died 2 weeks later when his temporary shelter collapsed during another storm. The clock was ticking. Japan controlled most of the Pacific. Every day, American forces delayed meant enemy fortifications grew stronger. But commanders couldn't push troops forward without solving the shelter crisis. Men can't invade islands if they're dying in their own camps. Military engineers across the country received emergency orders. Design housing that solves every problem simultaneously. Make it typhoon-proof. Make it handle 130-degree heat. Make it resistant to bombing. Make it quick to assemble because construction crews work under fire. Make it light enough to transport thousands of miles by ship. Oh, and you have weeks, not months. Most engineers looked at the requirements and said it was impossible. Physics doesn't work that way. Strong structures require heavy materials. Heavy materials can't be shipped quickly. Bomb-resistant designs take months to construct. Ventilation for extreme heat weakens structural integrity. Every solution created new problems. But tucked away in a Rhode Island office, one engineer stared at those impossible requirements and saw something nobody else did. George Fuller, an architect who'd spent 20 years designing industrial buildings, read the military specs 3 times. His colleagues had already dismissed the project as unsolvable. Too many conflicting demands. Too little time. Fuller pulled out a blank sheet of paper. He had an idea that would either save thousands of lives or end his career in spectacular failure. The military didn't know it yet, but their solution was about to come from a man willing to bet everything on a design so radical, so unconventional, that senior officers would call it insane. Would you trust your life to a shelter that looked like a tin can cut in half? George Fuller's phone rang at 2 a.m. on November 4th, 1942. Mr. Fuller, this is Colonel Peters, U.S. Army Corps of Engineers. We need you in Washington tomorrow morning. This is not optional. 12 hours later, Fuller sat in a classified briefing room with 15 other engineers. None of them knew why they'd been summoned. The mood felt tense, urgent. Colonel Peters didn't waste time with pleasantries. Gentlemen, we're losing men in the Pacific, not to combat, to weather and inadequate shelter. Current housing designs have failed across every metric. You've been selected because you represent the best structural engineers in America. Your assignment, design deployable housing that meets these requirements. He slid folders across the table. Fuller opened his. The specifications made his stomach drop. Requirements: withstand sustained winds of 150 plus mph, remain structurally sound during bombing, artillery, maintain interior temperature below 100 degrees Fahrenheit in tropical heat. Assembly time, under 1 hour by non-specialized crew. Weight, transportable by standard military ship. Cost, under $1 per unit. Production capacity, 0 plus units per week. Lifespan, minimum 5 years in harsh conditions. Timeline, 72 hours to submit initial design. An engineer next to Fuller laughed nervously. Sir, with respect, these requirements contradict each other. Strong structures need heavy materials. Heavy materials can't be assembled quickly. Ventilation systems that cool effectively compromise structural. I don't need excuses, Peters interrupted. I need solutions. We have 100,000 troops who need housing in active combat zones. Right now, they're dying in shelters that collapse, overheat, or get blown away. Your job is to fix that. Fuller stayed silent, but his mind was already working. The other engineers spent the next hour explaining why it couldn't be done. Too many variables, insufficient time, impossible physics. Fuller listened. Then he asked one question. Colonel, what's the single biggest killer, wind, heat, or bombs? Peters paused. Wind. Typhoons have destroyed more housing than enemy action, but heat casualties run a close second. Men pass out from heat stroke, become combat ineffective. Fuller nodded slowly. An idea was forming. That night, while other engineers argued about traditional designs, Fuller went back to basics. He sketched for 6 hours straight, filling pages with calculations and diagrams. Traditional military thinking approached shelter like a fortress, heavy, rigid, built to resist force with immovable strength. But what if that was wrong? Fuller remembered a project from 1938, an industrial warehouse he'd designed for a client who needed grain storage that could expand and contract with temperature changes. He'd used a semicircular design, corrugated metal ribs that distributed stress evenly. The building had survived a severe storm that leveled structures around it. What if he applied that principle here? By 3 a.m., Fuller had a rough concept. A prefabricated semicircular structure, self-supporting, made from corrugated steel. The curved shape would deflect wind rather than resist it directly. Corrugated panels would be lightweight but strong when curved. The design would ship flat, assemble quickly using simple bolts. For heat, he'd incorporate ventilation panels at both ends and a reflective coating to deflect sunlight. But here was the gamble. The structure would look nothing like traditional military housing. It resembled half of a giant metal barrel laid on its side. No corners, no flat roof, just smooth curves. Would the military accept something so unconventional? Fuller worked through the entire night, refining calculations. By morning, he had complete specifications for what he was calling the self-supporting steel structure, though history would later call it something else. He submitted his design at the 72-hour deadline. 11 other engineers submitted variations of traditional rectangular buildings with reinforced walls. Safe, conventional, proven technology. Fuller's design stood out like a spaceship among log cabins. 3 days later, Peters called him back to Washington. "Mr. Fuller, your design is unconventional. Some of my officers think it's ridiculous. One called it a soup can on its side." Fuller's heart sank. Peters continued, "But the structural analysis team says it might actually work. We're authorizing a prototype. You have 2 weeks to build a working model. If it survives our testing, we move to production. And if it fails?" Fuller asked. Peters looked him straight in the eye. "Then soldiers keep dying while we figure out something else. No pressure." Fuller had 14 days to build something that didn't exist yet. He assembled a team of metalworkers in Quonset Point, Rhode Island, a small naval construction facility most people had never heard of. The location gave the structure its eventual name, though nobody knew that yet. Day 1. Disaster. The first curved panel buckled during installation. The metal wasn't thick enough to support its own weight when lifted. Fuller watched 2 weeks of calculations crumble in 30 seconds. His lead fabricator, a man named Dutch Kowalski, shook his head. "George, the math might work on paper, but physics doesn't care about your blueprints. This thing's gonna collapse." Fuller didn't sleep that night. He recalculated every measurement, adjusted the gauge thickness, modified the rib spacing. By morning, he had a solution, but it required metal that was harder to source and more expensive. The budget was already tight. He made the change anyway. If the prototype failed, cost wouldn't matter because the project would be dead. Day 7. The first complete section stood upright. It looked strange, alien even. Workers stood back, skeptical. The curved walls seemed too thin, too flimsy. One strong wind and this thing would crumple like a soda can. Dutch walked around it twice. "I'll be honest, George. I wouldn't sleep in this during a storm." "You won't have to," Fuller said. "We're testing it tomorrow." That night, Fuller lay awake, wondering if he'd just destroyed his reputation. Every established engineer in America was watching this project. If his radical design failed publicly, he'd be remembered as the guy who wasted military resources during wartime while men died. Day 8. Testing began. The Army sent 3 officers to observe. They didn't look impressed. Colonel Peters arrived with a checklist. "Mr. Fuller, we're going to subject your structure to conditions matching Pacific theater environments. First test. Sustained wind load equivalent to 120 miles per hour. Industrial fans roared to life. The metal walls shook, panels rattled. Fuller's hands clenched into fists. 60 seconds, 90 seconds, 2 minutes of sustained pressure. The structure held. One officer made a note. No expression, no reaction. Test 2. Impact resistance. Simulated shrapnel and debris. They fired metal fragments at the walls using compressed air cannons. Each impact sounded like gunshots. Dents appeared in the panels, but nothing penetrated. Nothing tore loose. Fuller exhaled slowly. Test 3. Heat endurance. They sealed the structure and pumped in heated air until interior temperature reached 135 degrees. Then they measured how long it took to cool with ventilation panels open. 18 minutes to drop below 100 degrees. Peters made more notes. His face remained unreadable. Final test. Structural integrity under load. They placed sandbags inside weight equivalent to 20 men plus equipment. Then they tested whether the floor supports could handle it. No buckling. No stress fractures. Peters walked around the structure one more time. He knocked on the metal walls, checked the bolted connections, examined every seam. The other officers whispered among themselves. Finally, Peters turned to Fuller. "Mr. Fuller, I'm going to be honest. When I first saw your design, I thought it was the dumbest thing I'd ever reviewed. It looks like something a child would draw." Fuller's stomach dropped. But, Peters continued, it works. The engineering team confirms all stress points are well within safety margins. Assembly time clocked at 43 minutes with a 3-man crew. Material costs are $150 under budget per unit. He paused. However, I'm not the final decision maker. You'll present this to General Morrison and his staff in Washington next week. Fair warning, Morrison is old school. He fought in World War I. He trusts concrete and wood, not experimental curved metal tubes. One of the other officers spoke up. Sir, with respect, we don't have time for traditionalists to debate design aesthetics. Men are dying now. Peters shot him a look. That's exactly what you'll tell the general, if you can convince him. Fuller had 7 days to prepare a presentation that would determine whether his gamble saved lives or became a cautionary tale about innovation gone wrong. But there was something Peters wasn't telling him. 3 days earlier, another typhoon had hit Guadalcanal. 42 men dead, 200 injured. Every single shelter on the base destroyed. The military was getting desperate. Fuller never made it to Washington. On day 10, everything changed. Peters called at midnight. Fuller, plans have changed. General Morrison is approving immediate production. We're skipping the formal presentation. Fuller sat up in bed. Sir, what happened? Guadalcanal happened. We lost 42 men 3 days ago. Another storm hit New Guinea yesterday, 60 casualties. Morrison looked at the numbers and decided we can't afford to wait for committee approvals. Your design is going into production tomorrow. We need 500 units within 6 weeks. 6 weeks? Sir, we haven't even tested. I know, but here's the reality. We're losing more men to weather than combat in some zones. The president himself is demanding solutions. Your structure is the only viable option we have. Fuller's prototype became the blueprint for mass production overnight. The George A. Fuller Company factory in Pennsylvania converted 3 production lines to manufacture the curved panels. Workers operated around the clock 3 8-hour shifts, 7 days a week. But problems emerged immediately. The corrugated steel needed for the panels was in high demand across all military projects. Shipbuilders wanted it. Tank manufacturers wanted it. Aircraft factories wanted it. Supply couldn't keep up with demand. By week 2, production had only completed 127 units, way behind schedule. Factory managers were making difficult choices about which military projects got materials first. Fuller argued his case. These shelters will save more lives per ton of steel than almost any other application. A procurement officer shot back. So will the destroyers we're building. So will the tanks going to Europe. Everyone thinks their project saves the most lives. The military prioritized. Half the expected steel allocation was redirected to Fuller's project. The other half went to naval construction. It would have to be enough. Meanwhile, the first shipment of 50 completed units was loaded onto transport ships bound for Guadalcanal. The structures were disassembled, panels stacked flat, hardware packed in crates. Each unit weighed 8,000 pounds when fully packed heavy, but manageable for military logistics. The ships departed on December 2nd, 1942. They wouldn't arrive for 3 weeks. On Guadalcanal, conditions were deteriorating fast. After the latest typhoon, troops were living in makeshift tents that leaked constantly. Disease spread through camps because men stayed wet for days. Morale was collapsing. Commander Hayes, the same officer who'd survived the Espiritu Santo storm, received word about the incoming shelters. He was skeptical. Let me get this straight, he told his engineering officer. They're sending us curved metal huts that look like sliced soup cans? Yes, sir. The reports say they're typhoon-resistant and can be assembled in under an hour. Hayes laughed bitterly. I've heard that before. Remember those indestructible canvas tents? Lasted about 20 minutes in the last storm. But he didn't have better options. While the ships crossed the Pacific, Japanese intelligence intercepted communications about new American housing structures. They didn't understand the full details, but they knew something was coming. Japanese commanders on nearby islands began planning raids, targeting supply zones where the new structures would likely be assembled first. If they could destroy the shelters before they were deployed, it would damage American morale and slow base construction. The race was on. Could the shelters arrive, get assembled, and prove their worth before enemy forces struck? On December 18th, the transport ships entered Guadalcanal waters. Unloading began immediately. Crates stacked on the beach under armed guard. Construction crews assembled the first unit, while Japanese reconnaissance planes circled overhead, photographing everything. Hayes watched the assembly process. The curved panels bolted together faster than he expected. The structure took shape quickly, a smooth, rounded tunnel of metal sitting on a wooden platform. It looked flimsy, too lightweight, too simple. Hayes turned to his engineering officer. "Get men inside. I want it occupied immediately. If it's going to fail, better to find out now than during the next storm." 12 soldiers moved their gear into the first completed shelter. None of them knew they were about to face the ultimate test, and it wasn't weather. Japanese bombers were already preparing for a surprise raid scheduled for that night. The sky turned black at 11 p.m. Not from nightfall, from storm clouds, moving faster than anything Commander Hayes had seen before. The barometer dropped so quickly, his weather officer thought the instrument was broken. "Sir, we've got a Category 4 typhoon forming 60 miles offshore. It's moving directly toward us at 18 knots. Impact in approximately 4 hours. Hayes felt his chest tighten. They'd just finished assembling 20 of the new curved shelters. 20 experimental structures that had never faced real conditions. And now the worst storm in months was about to test them. "Get everyone to cover. I don't care where the new huts, old bunkers, anything with a roof. Move now." Across the base, soldiers scrambled. Some ran to the traditional reinforced bunkers built months ago. Others headed to the new metal structures, still skeptical but out of options. Private Danny Ortega stood outside one of the curved huts with his squad. Rain had already started heavy drops that stung exposed skin. "Sarge, you sure about this? Thing looks like it'll blow away." Sergeant Mike Crawford, the same man who'd survived the Espiritu Santo typhoon, made a decision. "We're going in. Those bunkers are packed full. This is what we've got." 12 men filed inside the metal structure. The interior was cramped but dry. Curved walls gave the space a strange feel like being inside a barrel. The wind picked up. By midnight, the typhoon hit full force. Hayes monitored from a reinforced command bunker as wind speeds climbed past 140 miles per hour. Rain came sideways. Visibility dropped to 0. The entire base shook. Through the chaos, he heard structures failing. The screech of metal tearing. The crack of wood snapping. Crashes as equipment went airborne. Inside the curved shelter, Crawford's squad huddled together as the storm raged outside. The metal walls groaned under pressure. Panels vibrated so violently it sounded like the whole thing would rattle apart. "This was a bad idea," Ortega shouted over the noise. "We should have stayed in the bunker." "Bunkers 200 yards away through 150-mile-per-hour wind," Crawford yelled back. "We'd be dead before we got halfway." The structure shuddered. A massive gust hit the curved roof, and for 3 terrifying seconds, the entire building lifted slightly off its foundation before slamming back down. Men grabbed onto support ribs, certain this was the end. But the metal held. The curved design did something traditional rectangular buildings couldn't. It deflected wind instead of resisting it head-on. The shape forced air to flow over and around the structure, rather than slamming into flat surfaces. Physics was working exactly as Fuller had calculated. Across the base, other shelters weren't as fortunate. 2 traditional wooden barracks exploded into splinters. A reinforced tent structure collapsed, trapping 8 men underneath. Medical tents vanished entirely, just gone, equipment and all. But the curved metal huts stayed standing. By 3 a.m., the storm's eye passed over. There was a brief, surreal calm. Hayes stepped outside the command bunker to assess damage. Devastation everywhere. Trees stripped bare, vehicles flipped over, supply crates scattered across the mud like toys. But those strange curved shelters still there. still intact. Hayes walked to the nearest one and knocked on the metal wall. "Everyone alive in there?" Crawford opened the door. His face showed exhausted relief. "Yes, sir. Structure held. Loud as hell and scary, but we're good." Hayes checked 6 more units. All occupied, all standing, not a single casualty inside any of the curved shelters. Meanwhile, casualties in traditional structures, 17 injured, 3 dead from collapsing buildings. As dawn broke, the full picture became clear. Every single one of Fuller's curved huts had survived with minor cosmetic damage, dents, scratches, nothing structural. Traditional buildings, 70% destroyed or severely damaged. Hayes immediately sent a message to command. "New shelter design successful. Recommend immediate mass deployment." But there was something Hayes didn't know yet. The storm had revealed the curved huts could survive wind. It had proven they could handle the Pacific's fury. But extreme wind wasn't the only threat. As the sun rose higher and temperature climbed past 95 degrees, men inside those metal structures began experiencing something Fuller's testing had missed. The curved metal panels, heated by direct tropical sunlight, turned the interior into an oven. By noon, soldiers were collapsing from heat exhaustion inside the very shelters that had saved them from the storm. The design had a fatal flaw nobody had anticipated. Private Ortega woke up confused. He was lying on a medical cot, soaked in sweat. A nurse stood over him, checking his pulse. His head pounded like someone had hit him with a hammer. What happened?" "Heat exhaustion," the nurse said. "You collapsed inside your shelter around 1 p.m. You're the 4th one today." Ortega remembered now. After the storm passed, his squad had stayed inside the curved hut, exhausted from the sleepless night. As morning turned to afternoon, the temperature inside climbed rapidly. At first, it was just uncomfortable, then oppressive, then unbearable. The metal walls absorbed direct sunlight and radiated heat inward. The curved shape that deflected wind so effectively also trapped hot air. Ventilation panels at both ends couldn't cycle air fast enough. By 1 p.m., interior temperature had reached 138 degrees. Ortega had passed out before he even realized he was in danger. Commander Hayes stood in the medical tent, furious. "How many casualties?" 11 so far, sir. 7 heat exhaustion cases like Ortega. 2 men with second-degree burns from touching interior metal surfaces. 2 more with severe dehydration." Hayes slammed his fist on a table. "So we've got shelters that survive typhoons but cook men alive in the sun? That's useless." The medical officer nodded grimly. "Sir, if we don't solve this heat problem, these structures are more dangerous than traditional tents. At least tents breathe." Word spread quickly. Soldiers refused to use the curved shelters during daylight hours. They'd rather risk being exposed than suffer heat stroke inside metal ovens. Back in Rhode Island, Fuller received an urgent telegram from Peters. "Shelter design causing heat casualties. Stop interior temps. Exceeding 135 f-stop need solution. Immediately stop production. Halted pending fix." Fuller felt sick. His design had worked perfectly against wind and rain, but he'd underestimated tropical heat conditions. The testing in Rhode Island had simulated high temperatures, but nothing like the sustained, brutal heat of Pacific sun beating down 12 hours a day. He'd saved men from storms, but created a death trap for sunny days. Fuller called an emergency meeting with his engineering team. They had days, maybe a week, before the military scrapped the entire project and looked for alternatives. "We need to solve the heat problem without compromising structural integrity," Fuller told his team. "Ideas?" His lead fabricator, Dutch, suggested painting the exterior white to reflect sunlight. Fuller ran calculations it would help, but not enough. Interior temps would still exceed 115 degrees. Another engineer proposed adding more ventilation panels. Fuller shook his head. "More openings weaken the structure's wind resistance. We'd be trading one problem for another." They worked for 18 hours straight, testing modifications on the original prototype. Every solution created new complications. Reflective coatings helped, but weren't durable enough for military use. They'd scratch off during transport and assembly. Insulation panels added weight and cost. Forced air ventilation systems required electricity that wasn't available at most bases. Fuller was stuck. On the third day, something unexpected happened. A supply officer at Guadalcanal sent a report that included observations from local islanders who'd been helping with base construction. The islanders had watched Americans struggle with heat in the metal structures. One of them, an older man named Tomas, had told the supply officer, "Your metal houses trap heat like cooking pots. We learned long ago you need air to move through, not just in and out, top and bottom, cross-flow." The officer hadn't thought much of it, but he included the comment in his report. Fuller read that single line 3 times. Cross-flow ventilation, not just end-to-end airflow, but vertical circulation that created continuous air movement. He grabbed a pencil and started sketching modifications. What if they added adjustable louvers along the bottom edge of the walls? Hot air rises if it could escape through existing top vents. While cooler air entered through bottom vents, it would create natural circulation without electricity. It was so simple, almost too simple. But would it work fast enough to save the project? Fuller didn't sleep for 4 days straight. His team fabricated modified ventilation panels with adjustable louvers positioned 18 inches above the floor. The theory was sound create a thermal chimney effect. Hot air exits through roof vents. Cool air draws in through bottom openings. Constant circulation prevents heat buildup. But theory and reality don't always match. They tested the modified prototype at noon on a brutal July day. Exterior temperature, 94 degrees. They sealed a thermometer inside and monitored interior temperature every 15 minutes. Without bottom vents, interior climbed to 127 degrees in 90 minutes. With bottom vents open, interior peaked at 103 degrees, then stabilized at 98. Fuller stared at the numbers. It was better, significantly better, but still too hot for men wearing full gear, working 12-hour shifts. Dutch walked up behind him. "George, it's not perfect, but it's survivable. That's what matters." "Survivable isn't good enough when men's lives depend on it," Fuller snapped. Then he caught himself. "Sorry, we're so close." They tried 17 different configurations over the next 2 days. Vent spacing, louver angles, cross-sectional airflow patterns. Each test brought marginal improvements. By day 4, they'd achieved interior temperatures of 91 degrees, in full sun 18 degrees cooler than the original design. Fuller sent the specifications to Colonel Peters with a note. Modified ventilation system reduces heat by 47%. Request authorization for field testing under combat conditions. Peters' response came 6 hours later. Approved. Modified units shipping to Guadalcanal immediately. Installation crews depart tomorrow. You're going with them. Fuller had never been in a combat zone. Never been under fire. Now he'd be installing experimental modifications while Japanese forces operated 15 miles away. The flight to Guadalcanal took 3 days, multiple stops, cramped cargo planes, 0 sleep. When Fuller stepped off the plane onto Henderson Field, the heat hit him like a physical force. Humid, oppressive, suffocating. Sweat soaked through his shirt in minutes. Commander Hayes met him at the airstrip. "Mr. Fuller, your shelters saved lives during the typhoon. Now let's see if you can keep men from dying of heat stroke." No pressure. Fuller's team worked around the clock, installing modified vent panels on existing structures and assembling new units with the improved design. The work was brutal, crouching in mud, handling metal panels that burned bare skin, constantly swatting mosquitoes the size of quarters. On the 3rd day, they completed the first modified unit. Hayes ordered a squad to occupy it during peak afternoon heat. Fuller stood outside with a thermometer, checking readings every 30 minutes. Noon, 89 degrees interior, 96 exterior. 1 p.m., 93 degrees interior, 90 no exterior. 2 p.m. 97 degrees interior. 101 exterior. The modified design was working. Men inside reported it was hot but tolerable, especially compared to the original ovens. But Fuller knew this was just one test. The real validation would come when hundreds of soldiers lived in these structures day after day, through varying weather conditions, under combat stress. On day 6, that test arrived in a way nobody expected. Fuller was installing louvers on the 8th unit when air raid sirens screamed across the base. Japanese bombers had been spotted approaching from the north. "Take cover," someone yelled. Men sprinted in every direction. Fuller froze, unsure where to go. A sergeant grabbed his arm and dragged him toward the nearest curved shelter, one of his own designs. They dove inside just as the first bombs fell. The ground shook. Explosions thundered close enough to rattle teeth. Through the open door, Fuller saw a fuel depot erupt in flames 200 yards away. Then he heard the whistle of a bomb falling close. Very close. The explosion hit 30 feet from their shelter. The blast wave hit like a truck. Fuller felt pressure crush his chest as the shockwave slammed into the curved metal walls. The entire structure rang like a bell, a deafening metallic clang that seemed to vibrate through his bones. Dirt and debris showered the roof. Something heavy crashed against the exterior. The walls flexed inward, then snapped back. But they held. For 10 seconds, Fuller couldn't hear anything except ringing in his ears. Smoke poured past the open door. Heat from the nearby explosion made the air shimmer. The sergeant next to him was shouting something, but Fuller couldn't make out the words. He checked himself. No blood, nothing broken. Alive. Outside, chaos continued. More explosions, anti-aircraft guns firing, men yelling orders, the metallic smell of burning fuel mixed with cordite. Fuller crawled to the door and looked out. A bomb crater sat 30 feet away, close enough that he could see the scorched earth, still smoking. Shrapnel had torn through wooden structures nearby, shredding them like paper. But the curved shelter barely had a scratch. A few dents, some dirt blown against the walls. Nothing structural. The curved shape had deflected the blast the same way it deflected wind, forcing energy to flow around rather than through. The air raid lasted 18 minutes. When the all-clear sounded, Commander Hayes emerged from the command bunker and surveyed damage across the base. Casualties: 6 wounded, 2 killed when a traditional wooden barracks took a direct hit. Hayes walked to the crater near Fuller's shelter. He examined the metal walls, running his hand over dents where shrapnel had struck. The curved panels had absorbed impacts that would have penetrated flat surfaces. "Mr. Fuller, did you design these to be bomb-resistant, or did you just get extremely lucky?" Fuller stood up, legs still shaking. "Honestly, sir, little of both. The curved structure distributes stress more evenly than flat walls, but I never tested it against actual explosives." Hayes nodded slowly. "Well, you just did, and it passed." Word spread fast. Soldiers who'd been skeptical of the strange metal huts now saw them differently. These weren't just experimental shelters, they were legitimate protection against multiple threats. Within 2 days, demand for the curved structures skyrocketed. Every base in the Pacific wanted them. Commanders who dismissed Fuller's design now sent urgent requests for immediate delivery. But production was still limited. The factory in Pennsylvania could only manufacture so many units per week. Steel allocation remained tight, and there was another problem nobody had anticipated. During post-raid inspection, Hayes' engineering team discovered something troubling. 3 of the shelters showed signs of stress fractures near bolt connections. Not failures, not yet, but weaknesses developing faster than expected. The engineering officer showed Hayes the cracks. "Sir, these structures are taking more punishment than they were designed for. Wind, heat cycling, bomb concussions. It's accelerating metal fatigue. Some of these bolted joints won't last 5 years, maybe not even 2. Hayes called Fuller over. "We've got microfractures developing at connection points. Your design handles individual threats well, but repeated stress from multiple sources is causing cumulative damage. Fuller examined the cracks. His stomach sank. He'd optimized the design for rapid assembly and cost efficiency, which meant bolted connections instead of welded seams. Bolted joints were faster to install, but created stress concentration points. How many units are affected? Fuller asked. Unknown. Could be dozens. Could be all of them eventually. Fuller's mind raced. If the structures developed systematic failures, the entire project could collapse. The military would lose faith in the design. Worse, soldiers could be injured or killed by shelters that degraded faster than expected. He needed a solution, but modifying thousands of bolted connections across the Pacific would take months and massive resources. Hayes crossed his arms. Mr. Fuller, I need straight answers. Are these shelters safe for long-term use, or are we sitting in future death traps? Fuller looked at the fractures again. They were small, barely visible, but they were real. Under the right conditions, they could propagate and cause failure. Sir, I need 72 hours to analyze the failure mode and develop a reinforcement solution. You've got 48, Hayes said. After that, I'm recommending we halt deployment until this is resolved. But there was something else. Something neither of them knew yet. Someone had been watching the shelters fail. And that person had plans of their own. Robert Haynes noticed the pattern first. He was a quality control inspector at the Pennsylvania factory, 47 years old, 20 years of manufacturing experience, known for catching problems before they left the production floor. On August 3rd, 1943, he flagged an entire batch of corrugated panels for inspection. The bolt holes were drilled 2 millimeters off specification. Not a huge difference, but enough to create uneven stress distribution during assembly. Who drilled these? Haynes asked the floor supervisor. Second shift crew. They've been running those specs for 3 weeks with no issues. Well, they've got issues now. These panels get assembled. Those misaligned holes will create weak points. Send them back for rework. The supervisor wasn't happy rework meant production delays, but Haynes had authority to halt any questionable output. 3 days later, Haynes found another problem. Metal panels with improper heat treatment. They'd pass visual inspection, but would fail under sustained stress. Then another batch. Ventilation, louvers with incorrect angle cuts. Too many problems. Too frequent. Too consistent. Haynes started documenting everything. Dates, shift assignments, specific defects. A pattern emerged that made his blood run cold. All the defective components came from second shift. All occurred on nights when the same 3 supervisors were on duty. And all the problems were subtle enough to slip past casual inspection, but serious enough to cause failures in the field. This wasn't accidental. Someone was deliberately sabotaging production. Haynes took his findings to the plant manager, a man named Carson, who'd been running the facility since 1938. Carson looked at the documentation. His face went pale. You're telling me someone's intentionally producing faulty parts for military equipment during wartime? That's exactly what I'm saying. And sir, we need to figure out how many defective units already shipped to combat zones. They launched a quiet internal investigation. Too public, and the saboteur might destroy evidence or flee. They needed to catch whoever was responsible and determine the full scope of damage. Over the next week, Haynes worked undercover on second shift, watching for anything suspicious. He noticed one supervisor, a man named Walter Drummond, spending unusual amounts of time near drilling stations, often alone. Drummond had worked at the factory for 8 months. His employee file showed prior experience in structural engineering. He'd applied for a design position 2 years earlier with the George A. Fuller Company headquarters. His application had been rejected. Haynes dug deeper. Drummond had submitted his own shelter design to the military in late 1942, a traditional rectangular structure with reinforced corners. The military had selected Fuller's curved design instead. Drummond had been bitter, vocal about it, told coworkers that Fuller's design was gimmicky nonsense that would fail under real conditions. But Drummond needed money. so he'd taken a supervisor job at the very factory producing Fuller's design. Every day, watching the curved panels roll off production lines, knowing his own design sat rejected in a file somewhere. Haynes reported his suspicions to Carson. They decided to set a trap. They fed false information to second-shift supervisors. A test batch of panels would be produced on Thursday night, marked with special codes, destined for high-priority deployment to newly captured islands. Only 3 people knew the real story: Haynes, Carson, and the security chief. Thursday night, Haynes watched from a concealed position. At 11:47 p.m., Drummond approached the drilling station when the regular operator stepped away for break. Drummond adjusted the drill press settings, subtle changes that would create off-specification holes. Then he moved to the heat treatment station and modified temperature controls. Security captured everything on camera. At 12:15 a.m., guards arrested Drummond on the factory floor. They searched his locker and found documentation showing he'd been sabotaging production for 4 months. His records indicated which batches were compromised and where they'd been shipped. Carson's hands shook as he read the list. Dear God, 87 units shipped to active combat zones. These could fail at any time. Worse, 3 days earlier, one of those compromised shelters had collapsed during a storm on Guadalcanal. 3 soldiers died. The military launched an emergency investigation. They needed to identify every compromised unit across the Pacific and replace them immediately, all while keeping the sabotage quiet to prevent panic and maintain troop morale. But there was a bigger problem. The compromised shelters looked identical to good ones. Without detailed manufacturing records, there was no way to tell which units were safe and which were death traps. Commander Hayes received the classified report on August 12th. His response was immediate. Inspect every single unit. I don't care how long it takes. Walter Drummond sat in military custody, facing charges that carried the death penalty: sabotage of military equipment during wartime, espionage, 3 counts of manslaughter related to the Guadalcanal deaths. During interrogation, Drummond showed no remorse. Fuller's design is fundamentally flawed, he told investigators. I was trying to prove that before more men died using inferior shelters. My design was superior traditional engineering principles. Proven materials. No experimental curves that concentrate stress. The interrogator slid crime scene photos across the table. 3 men crushed when your sabotaged shelter collapsed. Tell me how that proves your point. Drummond looked away. For the first time, emotion cracked through his defiance. That wasn't supposed to happen. The modifications I made shouldn't have caused complete structural failure. Something else must have. Stop. You don't get to blame your victims or make excuses. The trial lasted 4 days. Evidence was overwhelming. Drummond was convicted on all counts and sentenced to 20 years in military prison. But the damage was done. Across the Pacific, engineering teams scrambled to inspect thousands of shelters. The process was painstakingly slow. Each unit had to be partially disassembled to check bolt holes, panel thickness, heat treatment quality. Meanwhile, soldiers lived with uncertainty. Was their shelter safe, or was it a ticking time bomb waiting for the next storm? Morale plummeted. Some troops refused to sleep in the curved structures, preferring to take their chances in tents or foxholes. Commander Hayes faced an impossible situation. He needed those shelters. Traditional alternatives had proven inadequate, but he couldn't guarantee which ones were safe. Fuller arrived back at Guadalcanal on August 18th. He looked 10 years older than he had 2 months earlier. The sabotage had hit him hard, personally and professionally. How many compromised units have been identified? He asked Hayes. 43 confirmed so far. Probably another 44 still out there. We're working as fast as we can, but inspection takes time we don't have. Fuller spent 3 days developing a rapid field inspection protocol. Instead of full disassembly, inspectors could identify compromised units by checking 3 specific indicators: bolt hole alignment using a simple gauge, panel thickness at stress points using calipers, and heat treatment quality through hardness testing. The new protocol cut inspection time from 4 hours to 40 minutes per unit. Teams deployed across every Pacific base, working day and night. When they identified a compromised shelter, it was immediately condemned and replaced. By September 1st, all 87 sabotaged units had been located and removed from service. But Fuller wasn't satisfied with just fixing the immediate problem. He redesigned the bolt connection system entirely, eliminating the vulnerability Drummond had exploited. The new design used reinforced plates that distributed stress more evenly and were impossible to compromise through subtle manufacturing changes. Production resumed with enhanced quality control. Every panel now received triple inspection before shipping. Slowly, confidence returned. On September 15th, another major typhoon hit the Solomon Islands. Wind speeds exceeded 155 miles per hour, stronger than the storm that had first tested the shelters. Hayes watched from his bunker as the wind tore across the base. This time, 200 curved shelters stood in the storm's path. All of them had been inspected and cleared. All used the new reinforced connection system. The storm lasted 6 hours. When dawn broke, Hayes walked through the base. Damage everywhere, trees down, equipment scattered, traditional structures destroyed. But every single curved shelter stood intact. Not one failure, not one casualty among the soldiers who trusted the design. Hayes sent a message to Fuller, who was back in Rhode Island. Storm test successful. 0 failures, 0 casualties. Your design saved approximately 800 lives last night. Well done. Fuller read the message 3 times. For the first time in months, he felt the weight lift slightly from his shoulders. The sabotage had been devastating. 3 men had died because of one person's bitterness and pride. But the response, the re-inspection, the design improvements, the renewed commitment to quality had ultimately made the shelters safer than they'd been before. Sometimes, redemption comes through facing failure head-on and refusing to accept anything less than getting it right. But Fuller's trials weren't over yet. The military had one more test in mind, the most extreme environment in the entire Pacific theater, an island where everything tried to kill you. Iwo Jima was hell on earth. Black volcanic sand that burned through boot soles, sulfur vents spewing toxic gas, temperatures that climbed past 110 degrees in the shade, except there was no shade. And Japanese forces dug into tunnels so deep, bombs couldn't reach them. In February 1945, American forces invaded. The battle would last 36 days and cost nearly 7,000 American lives. But before Marines could fight, they needed a base. That meant shelters capable of surviving volcanic heat, ash storms, artillery bombardment, and typhoons, all on an island where every square foot was contested. The military called Fuller with an assignment that sounded like a suicide mission. We need your shelters deployed on Iwo Jima. You're going with the first engineering wave. Fuller was 52 years old. He'd never fired a weapon, never been in direct combat. Now he'd be landing on an active battlefield. He arrived on D+3, 3 days after the initial invasion. The beach was chaos. Artillery shells screamed overhead. Wounded men loaded onto evacuation boats, bodies covered with tarps. A Marine colonel briefed Fuller's engineering team. You've got a quarter-mile stretch of beach to work with. We need housing for 500 men operational within a week. Japanese hold the high ground and shell this area every few hours. Work fast, stay low, pray harder. Fuller's team started assembling shelters while artillery duels raged around them. The volcanic sand made everything harder it got, into bolt threads, jammed tools, made footing unstable. Worse, the heat was unlike anything they'd experienced. The black sand absorbed sunlight and radiated it back. Surface temperature measured 147 degrees at midday. On day 2, the first shelter was completed. Fuller watched as Marines moved equipment inside, setting up communications gear and medical supplies. 30 minutes later, men started stumbling out, dizzy from heat exposure. The ventilation system that worked perfectly in Guadalcanal couldn't handle Iwo Jima's volcanic conditions. Hot air rose from the ground and from the metal walls simultaneously, overwhelming the cooling system. Fuller checked the interior temperature. 126 degrees. "This isn't going to work," the Marine colonel said bluntly. "My men can't function in those conditions." Fuller felt panic rising. They'd solved the heat problem once. Now it was back. Worse than before, in the most hostile environment imaginable. That night, Japanese artillery found their position. Shells landed close enough to throw sand and shrapnel against the completed shelters. One explosion hit 15 feet from where Fuller crouched in a foxhole. He pressed himself into volcanic sand, feeling the earth shake with each impact. For 10 minutes, he genuinely believed he was going to die. When the shelling stopped, he crawled out and checked the shelters. Shrapnel dents, blast scoring on the metal, but structurally sound. At least they could survive artillery. They just couldn't keep men from cooking alive inside them. Fuller spent 2 sleepless nights calculating modifications. The problem was the volcanic ground radiating heat upward. Standard floor insulation wouldn't work too heavy, too slow to install under combat conditions. On day 5, Fuller tried something desperate. He had crews dig shallow trenches beneath each shelter and fill them with seawater-soaked sand. The evaporation would cool the ground, and the air gap would provide insulation. It was crude, improvised, completely untested. They modified one shelter and measured results. Interior temperature dropped to 108 degrees. Still hot, but survivable for men rotating through in shifts. "It's not perfect," Fuller told the colonel, "but it's the best I can do with available materials under these conditions." The colonel considered it. "Get me 20 shelters modified by tomorrow night. We've got a supply convoy coming in, and nowhere to store equipment." Fuller's team worked through another artillery barrage, through an ash storm that reduced visibility to 10 feet, through exhaustion that made men hallucinate. By the deadline, they'd completed 18 modified shelters. On day 8, the real test came. A massive storm system swept across the island, not quite a typhoon, but close. Wind speeds hit 95 miles per hour. Rain mixed with volcanic ash, creating a thick slurry that coated everything. Worse, Japanese forces chose that moment to launch a major counterattack. Artillery shells fell through the storm. Small arms fire cracked through the wind. Marines scrambled to defensive positions while the storm raged. Fuller and his team huddled in one of the modified shelters alongside 12 Marines. Outside, war and weather combined into something beyond comprehension. The shelter groaned under wind pressure. Ash slammed against walls. Explosions shook the ground. For 6 hours, they endured. The walls screamed. Metal flexed inward with each wind gust, creating a sound like nails on a chalkboard, amplified 100 times. Fuller watched stress points he'd reinforced back in Rhode Island being tested beyond any calculation he'd ever made. An explosion hit close, maybe 30 yards. The concussion wave slammed the shelter so hard, Fuller's ears popped. Dust and ash particles seeped through microscopic gaps in the door seal, creating a haze inside. One of the Marines, a corporal named Davies, gripped his rifle and stared at the curved ceiling. "Sir, is this thing gonna hold?" Fuller wanted to give a confident answer. Instead, he told the truth. "I don't know. It should, but I've never tested it against simultaneous wind, volcanic conditions, and artillery bombardment." "Great," Davies muttered. "We're the test." Another gust hit. The entire structure lifted slightly, maybe half an inch, before slamming back down. Several Marines cursed. But the bolts held. The reinforced connection plates Fuller had designed after the sabotage crisis distributed stress exactly as intended. The curved shape deflected both wind and blast waves. At 0200 hours, the storm peaked. Wind speeds climbed past 110 miles per hour. Rain came horizontal, mixed with ash that created a black paste coating everything. Fuller checked the thermometer he'd mounted inside. 89 degrees. The seawater-soaked sand trench beneath the shelter was working. Even in these conditions, even with volcanic heat radiating from below, The improvised cooling system kept interior temperature survivable. Around 0330, the wind started decreasing. By 0500, the worst had passed. Dawn revealed a landscape transformed. Ash covered everything 3 inches deep. Equipment, not properly secured, was gone, just vanished into the Pacific. 2 traditional supply tents had been shredded completely. But the 18 modified shelters stood intact. Fuller crawled out, legs shaking from exhaustion and adrenaline crash. The Marine colonel approached, covered head to toe in volcanic mud. "Mr. Fuller, I owe you an apology. When I first saw these shelters, I thought they looked like garbage cans. Now I'm recommending every forward position in the Pacific get equipped with them." Word spread fast. Combat engineers from other units came to examine the shelters and learn Fuller's modification techniques. The seawater-soaked sand solution was so simple, so field improvised, that it could be implemented anywhere with minimal resources. Within 2 weeks, modified shelters were deployed across Iwo Jima, then Okinawa, then dozens of smaller islands. The design that had started as one man's desperate gamble had become standard equipment for Pacific operations. But success came with a cost Fuller hadn't anticipated. On March 8th, he received news that hit harder than any artillery shell. Private Danny Chen, the soldier whose mother never received his letter about the Espiritu Santo typhoon, had a younger brother serving in the Pacific. Lieutenant James Chen had been killed on Iwo Jima, not by enemy fire, but by volcanic gas exposure while sleeping in one of the early, unmodified shelters. The ventilation system hadn't been adequate to clear sulfur dioxide that seeped up from ground vents at night. Fuller read the casualty report in his temporary quarters. His hands shook. James Chen had survived the fighting. Survived artillery barrages and small arms fire. Then died from toxic gas in a shelter that was supposed to protect him, a shelter Fuller had designed. The modified version with improved ventilation came 3 days too late to save Chen's life. Fuller sat alone that night, staring at design schematics scattered across his desk. He'd saved hundreds, maybe thousands of lives. The shelters had proven themselves in the worst conditions imaginable. But they hadn't saved everyone. Some nights, that truth was hard to carry. A Marine chaplain found Fuller sitting outside at 0200, unable to sleep. The chaplain sat down without asking permission. "I hear you're the engineer behind these shelters." Fuller nodded. "You know how many men are alive right now because of your work?" "I've been counting. Last month's typhoon at Okinawa. 0 casualties among troops in your shelters. Conventional housing, 17 dead. That math matters. Tell that to Lieutenant Chen's family," Fuller said quietly. The chaplain was quiet for a moment. "War doesn't give us perfect solutions, Mr. Fuller. It gives us impossible problems and asks us to do our best with what we've got. You did that. Some men died anyway. That's the nature of this hell we're living through. But a lot more men are going home because you refused to accept failure." Fuller didn't respond. He just stared at the distant horizon, where artillery flashes lit up the night sky. The chaplain stood to leave, then paused. "One more thing." Chen's family wrote to command. They asked that his brother's death not be in vain. Requested that findings from the incident be used to improve shelter safety. Your modifications came directly from that investigation. James Chen's death led to changes that saved others. End quote. Small comfort, but comfort nonetheless. By April 1945, over 160,000 of Fuller's shelters had been manufactured and deployed. Production had become so streamlined that assembly time dropped to 37 minutes with a 3-man crew. The war was turning. Victory felt possible. But Fuller's story and the shelter's legacy had one more chapter to tell. August 15th, 1945, Japan surrendered. The war was over. Fuller stood on Okinawa when the announcement came through. Around him, Marines cheered, fired weapons into the air, embraced each other with tears streaming down their faces. He felt relief, exhaustion, but not celebration. The numbers haunted him. Over 160,000 shelters produced. Approximately 840,000 soldiers had used them at various points during the Pacific Campaign. By military estimates, the curved metal structures had prevented roughly 3,200 deaths from typhoons, heat exposure, and enemy bombardment compared to traditional housing methods. 3,200 lives saved. That should have felt like triumph. But Fuller couldn't stop thinking about the other number. 47. 47 confirmed deaths directly related to shelter failures. 3 from Drummond's sabotage. 11 from early heat-related problems before modifications. 16 from the volcanic gas issue on Iwo Jima before ventilation improvements. 17 more from various structural issues, assembly errors, and unforeseen circumstances. The military considered it an acceptable ratio. 47 deaths versus 3,200 lives saved. That was a success by any wartime metric. Fuller wasn't so sure. He returned to Rhode Island in September 1945. The factory had already shifted production to civilian applications, emergency housing for returning veterans, temporary structures for displaced populations, industrial warehouses. The Quonset Hut, as everyone now called it, had become famous. Newspapers ran stories about the revolutionary design. Fuller received commendations from military brass. His company's stock value tripled, but at night he'd wake up thinking about Lieutenant Chen, about the 3 men crushed in Guadalcanal, about every single one of those 47 casualties. His wife, Eleanor, found him at his desk one night in October, surrounded by casualty reports. "George, you need to sleep. I keep running the numbers. If I'd tested the heat system more thoroughly before deployment, 11 men would still be alive. If I'd anticipated volcanic conditions, 16 more. Stop." Eleanor put her hand on his shoulder. "You can't redesign the past. You made the best decisions you could with the information available at the time. That doesn't bring them back." She was quiet for a moment. "No, it doesn't. But torturing yourself doesn't honor them either. You know what does? Making sure their deaths led to something better." Fuller looked up at her. "What do you mean?" "Every modification you made came from learning what went wrong. Those improvements are now standard practice. Future emergency shelters will be safer because you refuse to ignore failures. That's how you honor the men who died, by ensuring their sacrifice taught lessons that protect others." Fuller wanted to believe that. He really did. In November, the military launched an official investigation into wartime shelter performance. Fuller was called to testify before a review board examining equipment effectiveness across all theaters. The questions were pointed. Clinical: how many units failed? What percentage experienced structural problems? Were shortcuts taken to meet production deadlines? Fuller answered honestly. He provided every detail about failures, modifications, and lessons learned. He didn't minimize problems or make excuses. When the questioning ended, a general on the review board spoke. "Mr. Fuller, this board has reviewed testimony from hundreds of equipment contractors. Most spend their time defending decisions and shifting blame. You're the first who's focused entirely on what went wrong and how to prevent it. That's the kind of accountability we need." The final report commended the Quonset Hut design, while recommending several improvements for future deployments. It noted the 47 casualties, but concluded that rapid wartime innovation inherently involves trial and error under combat conditions. The Quonset program's success rate exceeded expectations for experimental technology deployed at scale. Fuller read the report twice. The words felt hollow. Success rate. Acceptable casualties. Statistical analysis of human lives reduced to percentages and ratios. On December 3rd, 1945, Fuller received an unexpected visitor at his Rhode Island office. Sergeant Mike Crawford, the man who'd survived both the Espiritu Santo typhoon and the first Guadalcanal shelter test. Crawford had been discharged and was heading home to Nebraska. He'd stopped specifically to meet Fuller. "Mr. Fuller, I wanted to thank you personally. Your shelters saved my life, twice. Once during a typhoon that killed men in traditional barracks 20 yards from where I was. Once during a bombing run that turned wooden structures into shrapnel while I sat safe inside curved metal walls. Fuller shook his hand, unsure what to say. Crawford continued, I heard you've been beating yourself up about the men who died in early failures. Sir, with respect, don't. War kills people, that's what it does. But you gave thousands of us a fighting chance to come home. My daughter gets to meet her father because of you. That matters. Crawford left. Fuller stood alone in his office, staring at the doorway. Maybe Eleanor and Crawford were right. Maybe the measure of success wasn't perfection, it was whether you learned from failure and kept trying to do better. But there was something Fuller didn't know yet. Something the military had classified and wouldn't reveal for another 30 years. The shelters had one vulnerability that military brass deliberately kept secret during the war. Fuller thought he knew everything about his shelters. He was wrong. In March 1944, while the war still raged, a military testing team at Aberdeen Proving Ground in Maryland conducted classified experiments. They fired various weapons at Quonset Huts from different angles, measuring penetration, blast effects, and structural failure modes. Most results confirmed what Fuller already knew. Horizontal artillery fire? Deflected. Shrapnel from nearby explosions? Minimal damage. Wind and pressure waves? The curved design handled them brilliantly. But test number 17 changed everything. A mortar crew fired shells in a high arc, dropping them straight down onto the curved roof. The first shell hit the apex, the highest point of the curve. The metal roof punctured instantly. The shell detonated inside. The entire structure collapsed within seconds. They ran the test 6 more times with different shell sizes. Same result every time. Direct overhead impact at the curve's peak was catastrophic. The testing officer wrote in his report, Quonset Hut design demonstrates critical vulnerability to plunging fire. Recommend immediate roof reinforcement or tactical deployment protocols to minimize exposure. That report went straight to classified archives. No roof reinforcement was ordered. No design modifications made. No tactical protocols changed. Fuller never received the report. Never knew the tests had happened. Never got the chance to fix the problem. Why the cover-up? Because military intelligence had intercepted Japanese communications showing enemy artillery tactics focused on horizontal fire patterns. They weren't using plunging mortar attacks against housing areas, they were targeting them with direct fire artillery. If the vulnerability became widely known, it might leak to enemy forces. Japanese commanders might shift tactics specifically to exploit the weakness. Hundreds or thousands of additional casualties could result. So military brass made a choice. Classify the information. Accept limited casualties from mortar fire, rather than risk widespread tactical changes by the enemy. It was cold, calculated, ruthless, and by the numbers, probably correct. Between 1,944 and 1,945, 11 American soldiers died from direct mortar hits on Quonset Hut roofs. Tragic losses, but intelligence estimates suggested that if Japan had systematically targeted the vulnerability, casualties could have reached 300 or more. 11 deaths to prevent 300. The military considered it an acceptable trade, but they never told the families of those 11 men. Never explained that their sons or husbands died from a known flaw that could have been fixed. The secret stayed buried for 32 years. When the documents were finally declassified in 1976, veterans groups erupted in anger. Families demanded answers. How could the military knowingly deploy flawed equipment and hide the truth? The Pentagon's response was clinical. Wartime operational security required classification of tactical vulnerabilities. Disclosure would have endangered more lives than it protected. Technically true, morally complicated. Fuller was 73 when he learned about the tests. He read the Aberdeen Proving Ground report in stunned silence, seeing test data and failure analysis he'd never been allowed to see during the war. He could have reinforced that roof, added a double-layer design or internal support ribs. It would have added cost and weight, but it was doable. Instead, 11 men died while he remained ignorant of the flaw. The question that haunted his final years: was the cover-up justified? The classified document was declassified in 1976. Fuller was 73 years old when he finally learned the truth the military had hidden for 3 decades. The Quonset Huts had a critical weakness: direct mortar fire from above. The curved roof, so effective at deflecting horizontal blast waves and wind, was vulnerable to projectiles dropping straight down. A mortar shell hitting the apex of the curve could penetrate and cause catastrophic failure. Military strategists knew this by mid-1944. They'd run tests, the results were clear, but they never told Fuller, never modified the design, never warned the troops. Why? Because the vulnerability was so specific that revealing it would have given enemy forces a tactical advantage. Japanese commanders might have shifted artillery tactics to exploit the weakness. More men would have died. So the military made a calculated decision: keep it secret, accept the risk. The shelters still provided better protection than alternatives, even with this flaw. Fuller read the declassified report in his living room. His hands trembled. 11 soldiers had died from direct mortar hits on shelter roofs during the war. 11 deaths that might have been prevented if he'd known about the vulnerability and redesigned the roof structure. But would more have died if the enemy had learned to exploit it systematically? There was no way to know. No way to calculate that moral equation. Fuller never spoke publicly about the classified document, but he spent the last years of his life consulting on emergency shelter design, always pushing for transparency, always insisting that engineers needed complete information to make the best decisions. He died in 1981 at age 78. By then, the Quonset Hut had become a permanent part of history. The basic design influenced everything from Arctic research stations to refugee housing to disaster relief shelters used by the Red Cross. Today, when hurricanes hit, emergency crews still deploy curved metal structures based on principles Fuller developed 80 years ago. When earthquakes destroy cities, relief organizations use modified Quonset-style shelters because they're quick to assemble and structurally resilient. The original wartime huts? Many still stand. Repurposed as storage buildings, workshops, even homes. Drive through rural America and you'll spot them, those distinctive curved metal structures, often painted, sometimes modified, but unmistakably descended from Fuller's desperate wartime gamble. The lessons learned went far beyond engineering. Fuller's story taught military procurement that rapid innovation requires accepting failure as part of the process. That perfection is impossible under wartime pressure. That transparency about problems leads to better solutions than covering them up. It taught that individual courage, one engineer willing to propose something radically different, can save thousands of lives. And it taught the hardest lesson of all: success and failure aren't opposites, they're intertwined. The same design that saved 3,200 lives also failed 47 times. Both truths exist simultaneously. The Quonset Hut wasn't perfect. It never could be. But it was good enough when it mattered most. Sometimes that's the best any of us can do: create something imperfect that still makes a difference. Learn from every failure, and trust that the lessons will help someone else down the line. Fuller's curved metal shelter started as an impossible assignment with a 72-hour deadline. It became a legacy that's still saving lives today. Not bad for a tin can laid on its side.